Welcome, class! I am absolutely thrilled to be your professor today for this explainer. We are finally going to bridge that gap between simple introductory physics and the beautifully complex mechanics of the real world. You know, up until now, we've kind of treated everything as a simple little dot on a graph. But today we step into reality. So let's just dive right into this by shattering a little illusion your previous physics teachers might have told you. Because real objects, things like wheels, spinning tops, planets, they have actual size, they have shape, and they definitely don't just move in perfect straight lines. They warp, they bend, and most importantly for us, they rotate. The idealized point mass model, it completely fails to capture this motion. So we need to adopt a totally new framework, the rigid body model. All right, here is our masterclass syllabus for today's explainer. Number 1, beyond the point mass. 2, the center of mass. 3, torque and rotation. 4, moment of inertia. 5, conserving angular momentum. And 6, final exam strategies. We're going to move step by step from the basics all the way to the supreme laws of conservation. Section 1, beyond the point mass, moving from the illusion to reality. We've got to first establish the really critical differences between translational motion and rotational motion. Okay, picture this. A sliding block only has pure translation, meaning literally every single point on that block is moving with the exact same velocity at any given instant. But introduce a rolling cylinder or a spinning ceiling fan, and boom, you have rotation. This is a game changer because it means individual particles within the body are actually traveling at completely different velocities. Think about it. A particle way out on the outer edge of a fan blade is moving so much faster than a particle right near the central pivot. Make sense? Moving right along to Section 2, the center of mass, the ultimate physics hack. To handle these extended bodies, where, remember, every particle has a different velocity, without going completely crazy, physicists use this brilliant mathematical shortcut. The crucial takeaway here is that we can separate the motion of a highly complex system into 2 totally manageable pieces. We take the simple translational motion of its center of mass and just add the rotational motion happening around that center. This little trick allows us to treat a tumbling, spinning object flying through the air just as simply as we treated those basic point masses in your earlier classes. Now, don't panic about the math. By leveraging reflection symmetry and realizing that internal forces always cancel out in action-reaction pairs, you can vastly simplify things. You can beautifully turn what looks like a terrifying calculus problem where we have to transition from summing up discrete mass particles to doing continuous mass integrals into a simple, comforting little geometry puzzle. Take an L-shaped lamina, for instance. You just break it down into 3 basic squares, find the center of those, and average them out. Honestly, you've totally got this. I absolutely love this firework projectile analogy because it provides the perfect visual intuition. Just imagine a firework exploding midair. No matter how violently the internal particles blow apart in every conceivable direction, the internal forces cancel each other out completely. So the system's center of mass? It just calmly continues on its original parabolic path, completely and utterly unaffected by the explosion. All right, Section 3, torque and rotation. Spinning things up. Now that we have the center of mass securely defined, we have to talk about what actually causes a rigid body to spin in the first place. If you've ever tried to open a heavy door by pushing right near the hinges instead of the handle, you've experienced torque firsthand. It is incredibly difficult, right? And that's because torque isn't just about how hard you push. It's about exactly where and at what angle you apply that force relative to the axis of rotation. Using a wrench to turn a stubborn bolt works on the exact same principle. So let's build a repeatable, step-by-step process you can use on your final exam to conquer absolutely any complex rigid body system. First, you isolate the center of mass translation using Newton's second law. Then, you calculate the internal twisting forces using the cross-product rule for torque. And hey, quick tip, always remember to physically curl the fingers of your right hand from the radius vector toward the force vector to find your torque direction. That right-hand rule is a lifesaver. Section 4, moments of inertia, the rotational analog to mass. We all know that mass resists linear acceleration. Like a heavy box is super hard to push, right? But what resists rotational acceleration? Well, what's crucial to understand here is that the moment of inertia is not just a fixed, static number for a given object. If you change the axis of rotation, you completely change the inertia. This is exactly why a solid cylinder and a hollow sphere, even if they have the exact same total mass, behave so differently when rolling down a ramp. The hollow sphere has all its mass distributed much further from the center, which gives it a much higher resistance to rotation. This direct comparison is pure gold. It maps your existing knowledge of linear kinetic energy perfectly onto our new rotational paradigm. Literally every concept you've already learned about force and mass has a direct one-to-one mirror in the world of torque and moment of inertia. It's like learning a new dialect of a language you already speak. Section 5. Conserving angular momentum, the beauty of the spin. Just as linear momentum is strictly conserved in a closed system without external forces, rotational motion has its own supreme conservation law. Listen up, class, because this is without a doubt one of the most beautiful and highly testable principles in all of physics. If no outside twisting force is applied to a system, its angular momentum remains absolutely constant. Whether you're in the lab analyzing a bicycle rim spinning on an axle to demonstrate precession, or you're looking through a telescope at massive binary stars dancing in deep space around a common center of mass, or even just watching an ice skater on a rink, the conservation of angular momentum governs them all. That skater is the absolute classic example. By pulling her arms in tight, she decreases her moment of inertia. And to conserve her total angular momentum, her rotational speed has to dramatically increase. It's math in motion. Finally, Section 6, Final Exam Strategies, Surviving the Test. Let's wrap up this explainer by giving you the ultimate survival guide. Take a mental picture of this summary table right now. Directly mapping linear variables to their rotational counterparts is by far the fastest way to memorize your formulas. I mean, if you know Newton's F equals ma, you automatically know torque equals moment of inertia times angular acceleration. It's the exact same mathematical poetry, it's just spinning. Okay, listen closely, because this right here is where most students end up losing points on the final. Please remember that internal forces always cancel out. Do not let a tricky exam question bait you into factoring them into the total system momentum. Also, be extremely careful to distinguish between pure fixed axis rotation, like a ceiling fan, versus a sweeping oscillation, like a pedestal fan moving back and forth. And never, ever forget that torque is a vector product that strictly obeys the right-hand rule. Get that right hand out during the test if you have to. So I'm going to leave you with a rather provocative thought to ponder. If all forces within our universe are internal, what exactly dictated its initial spin? Master these concepts, use your notes as your guide, and until next time, keep exploring the physics of the incredibly complex world around you.